So we got to think we have quite a flexibility in the kind of data we can look at. So when the input side here, first we have the images, we have three-dimensional classes, time series, what we already call correlations, narratives, and everything. So oftentimes what we always said, now we got a little bit more into it. So what is resistance capturing and how do we change it? So as a very easy thing for a one-dimensional function, it's always this, we have this filtration, either way going up and look at certain sublevel sets. So we're increasing the function value and then look at everything which is below there. And here in color, the connected component according to this sweep we have. And then we match certain points. So at minimum, they're born, at maximum, components merge. And then we have this persistent paradox. And the idea was, instead of looking at one specific time, we can use this sweep to tell us more about the data and also simplify it. So we get this persistence, which depending on what we're looking at, oftentimes we find as the difference in function values for these different, for the minimum maximum range. So we get these persistence barcodes. Barcodes on So both are like equivalent representations. So oftentimes in 2D, the sweep would look like this. That we have our elevation map, and then we go through and check what are the connected components, how is this evolution done, and then we can match it. So now on the map where exactly it's Zastosowań, that's maybe something else for people who know read that. I think this is now I'm just looking at here is the level set for elevations between 800 and 1000. I think that's where Zastosowań should be. So one of these regions there we see Zastosowań. But if we just look now, see, okay, we're interested in the peaks and we go down. Because the very traditional way to think about resistance is we measure prominence of peak. So if everything is quite high, then the prominence, which we term persistence, is a bit large, is small for most of them, and then just for one big peak. Then if we're interested in the peaks and look at all the persistence pairs, these are, so here I'm all the white points, you can't see it there, all the white points are components where locations where components are born, the green points where they vanish. But this, if you look at this is a map where we would have trouble understanding what exactly are we looking at, what are features which might be important. So we can use plots where we say, okay, we cross show by persistence and look at how many points do we have. How does that look like? And this is often termed as a mean. So around here we can threshold persistence. And then look at this diagram here. I rotated it, so this is a bit what we use for landscape. So here is birth time, and this is the lifespan, which is this death time minus birth time. And then we would just get these fewer points. Where we can then say, well, here we can have the origins, where is it born, where is it dying. And this shows us a bit more of more prominent features of the peaks in these different kinds of regions. So this type of ideas and this pipeline help us understand a bit more how can we extract information about the material we're looking for and also filter out maybe noisy things. So we don't have to do Gaussian filtering on certain noise signals, but we can also get a segmentation from the persistence pipeline. Just for a slide for mentioned database, this would be backing curves and then your Euler probability for the same. Okay, so pipeline for data looks like that. Then we get some surface areas. We extract the digital images, the elevation map, we get a cubical complex, the persistence diagrams, and then for machine learning we can then say extract backing curves. Persistence statistics on the diagram. This is Niklas already mentioned. And luckily here we can't directly run certain statistics, so we need to have certain vector representations for that. But we can also use the persistence diagram to filter out certain features we do not care about, and then do the same thing and improve the results. In particular, improve our understanding of, okay, if I'm looking at a machine surface, it might be more interesting for one, what is the direction of symmetry? For another, what are prominent peaks, data values? And for that, the stays and values, short peening is prominent one. So for short peening, you often do that when you have want to strengthen a certain material in a certain way. And it works by shooting a lot of steel balls on top of the surface. And due to this strength, to this impact, they strengthen the material by having this compression forces. And that works quite well. Also in applications, for example, for medical applications where you might have some metal in your bone that you have for fix a broken leg. You need to implement it, and the question there is this offset. You, on one hand, want to have it that bacteria have trouble adhering to the surface, and on one hand, that it is better accepted in your bone, that there is nothing major in there. There you can see that depending on how long you keep on shooting the surface, that there is an impact on the bacteria adhesion, as well as how well it is accepted as a bone replacement profit. So one of the problems for short peening is that you can't really control so much about the coverage percentage, which is how much of the surface has been impacted. But we have to see these compressions, because oftentimes you're shooting the balls in there, small balls, and oftentimes they just think, okay, we keep on shooting until a certain time, and then we roughly say coverage percentage is something like that. But for experiments, you want to have a better handle on, does coverage percentage influence your specific findings? And so now we use for quantifying this change, now this is more of a numeric example, we will compare TDA to conventional surface level. Conventional surface level, this is a lot of the times they want one key value. So a lot of statistical things you can use, but also other things which work on these profiles and pipelines as well. That's not really, I think, the important thing that we will be using in particular or comparing to is skewness, and one which is still used a lot, even though it has a lot of drawbacks, which is this arithmetic mean height, which is just the height of the space. So for numerical experiment, which we compare to, we had a simulation, but they started with a random placement of shots, and then they kept on repeating on this random placement, adding more and more, and then average the coverage percentage. It's 100 here because we have it that there is a circle in here, so not the whole image, but the circle in here, and there in this circle we measure the coverage, so that where the shots are placed. That is due to the simulation used. In one of these sequences, this is built on top of each other for this placement, and here the sequence is different. But the number of shots, the number of things are kept in order, and the coverage percentages are then roughly in certain bits. So for the normal surface area, so we look at the left, the arithmetic mean height or skewness. We are now comparing all these different things where we have the coverage classes, and for arithmetic mean height, we see, okay, it increases and then it stops, because if we hit more and more, the peaks are getting lower, so the deviation, the displacement is getting smaller, and so this goes down again. But if we would like to classify, distinguish different coverage classes to each other, it would be problematic even from 88%. So after a while, we can't really distinguish them when we use just this one scalar value, so skewness is performing better, but there's still quite a large overlap between the classes. And this is an easy case in the sense that we know, oh, there's impact size, so hopefully our parameters that we use for larger surfaces should reflect that. So then we can use persistence. For example, we already heard something about persistence entropy, so we can use this entropy function on the lifespans, normalized lifespans for the persistence diagram with this kind of graph. So even if we just use one scalar value, we see this is nicely clustered because more or less it captures the information of, okay, we roughly have this amount of these. This is captured in entropy, or you can also see it for the Betty curves, now in 0 dimension, for super level set, that we see that this feature here in the middle, for a certain threshold just below 0, is really nicely distinguishing these. So in a pipeline, obviously we don't use one scalar, instead of a couple of them, and then we can compare conventional parameters, so about 20 of them, against the persistence features, and we can see here I just use different kinds of clusters to see if we do model fitting and try to find the best ones, how are they different for these, and you can see that for persistence-based features we are quite good. Here maybe for the decision tree we have a bit more of a span, but still it's even in the lower end, it's nearly on that level. So that works quite well on numerical data. Obviously, the question is how does it work for real? How would it work for real data? And is it still distinguishing this? So I see. So here we look at a certain plot, this notched area, where we have smooth area in this direction, an upward and a downward direction. So smooth can be more or less considered as a reference area, and the notched areas are of interest, and so they are shooting this this specific material, and now we are considering them with 3 different questions, which would be, can we distinguish the different directions? Because here it's a different thing for that, depending on how the shots are placed. So we have different angles, and we fixed one, which is not completely fair, but a little bit slighted, so that there should be a difference between upwards, downwards direction, and the smooth one. And then there are also different heat treatments to see, is this, so the goal of this experiment was also to then stress this material until it's breaking, and then we would find the breaking. Here are just heat treatments which we have, which are labeled. I didn't show it here. So here it's really we have the smooth one with the heat treatment, untreated, downward upwards, and SP1 means like normal shock cleaning for a certain time, and SP2 is they increase the shock cleaning to go even further, so which we would term 1000%. So it means that they take the time for a surface to be 100% covered, roughly, and then they just use 10 times the time and then explain, then say, okay, this is 1000% covered. And we can see that if we say, okay, can we classify the direction of the notch cover for all the different ones? Then the TA scores are far better in classifying the different directions we've seen in the material than the classical ones, as well as if we consider can we put that into different post treatments for the materials. So it's really capturing also the information we have for actual material to say, okay, how is that affecting it? And as I already shown before, we can also use that to understand the material a bit better because we can visualize it better. So we can really do simplifications and show what are we really seeing, what might be interesting regions, and how is that affecting. Obviously, we can also do that in 3D, but then this, so here the nice thing would also be, this is a note, you would always need a reference surface. So for the example that I showed, it was mostly like plane filling, because we just had an elevation map in reference to plane. But here we would use ellipsoid, an ellipsoid in here, and then match the displacement from this nuclei to this ellipsoid. So depending on your application, it might be something different. And then we could compute resistance directly, and the nice thing is we also inflect that we have this border where it's matched. So we have a really thing. We can either do it directly using physical contacts. Okay. And so just a major thing. So it helps distinguish surfaces, but it also I didn't go into detail too much now, is help us visualize and understand it by doing these visualizations of where are certain regions of interest, or what shall we do differently. And so it's also nice in these different situations that we're quite flexible in the input we can get and the input we can. So thank you very much for listening. I think we just have good time to do that.
Thank you very much.
Well, I have questions. In your 3D example, have you tried using resistant homology transform or other characteristic transform?
Yes.
Okay.
So it's like
what was the result?
So so it wasn't performing so much better than what I already had, but I must say, I was comparing it to the TDA example, I already got a 95%, 96% accuracy. So that was more of the sort of bigger problem for that was you really have to do it more in the segmentation that you find what's the good approximation of the nuclei if you have a noisy image, or depending on how your data is presented. So that is then a little bit more prone for being affected by this noise. While if I'm just looking at the image and using TDA on there, I can always filter it out. So that was more of an afterthought, because after I'm doing more pipeline, getting thresholds, then I can segment it so I can say, okay, on top of that, but yeah, let's consider about that.
Can you maybe try to the microphone actually? Yeah, so I'm also curious when you're talking about going to 3D in the sense that if I understand this, I mean that you approximate this, like you said, the surface, right? Not as a flat surface, but as a sort of three-dimensional reference surface. Have you thought about going further and maybe trying to compute the conductivity of like a porous medium, or essentially you really go or it's like three-dimensional in the sense that you can't approximate the material as the surface.
What I can show a picture for. So if we're gonna go and so when we go a bit more to 3D, so let's go with so now we can maybe talk a bit more when you said that about the porous material. And so we can on one hand, it's like what I showed, it's like obviously then I need to know the shape I want to go with reference surface and the displacement. But what we can also do is indirectly use this 3D representation. This comes from images, so it's more of a set of images, and then I can directly consider the cubical context on that, and then see about connectivity in there. So what we, depending on my masking, we would nicely see this kind of, we take into account once the bone structure, as well as wherever we are painting. So here, these blue dots would be lacuna, which we're of interest in that regard. So that's, we can also add more layers than look at that. So we don't not only limit it on this reference surface, also for core structures might be more interesting to say we have a certain mapping or masking. And on this mask, we still use functions, filtration functions, and consider that of interest. I'm not sure if that. Obviously, I'm not showing that, but obviously, as a fun example, you can distinguish different patches and mountain regions. Because and then think about, okay, well,